Okay, so the last three of the 9 famous functions. So the absolute value function, we don't use it that often, but sometimes when we're looking for a different kind of graph or a different kind of function, this is a easy one for us to talk about. It's very easily calculated, right? We know what the absolute value is. It's the distance from 0. So again, an absolute value of negative 2 would just be 2, 1, 0, 1, and 2. Okay. So we graph it, and we should get that familiar V shape. Okay. Again, you should know fairly quickly domain. All x's, all values for x can be inputted, so the domain is all real numbers. The range, right, when you take the absolute value of a number, you never get a negative, so the range is not down here in the negatives, it starts at 0. Okay, continues on through infinity. Okay. Reciprocal function, we use this a little bit later on at the beginning of chapter 4. But again, it gives us a feature of a graph that we don't see with the other 9 famous functions, and that's an asymptote that you'll see. Clearly, right away, you should realize that for this reciprocal function, remember, you can't plug in 0, okay? Because 1 over 0 is undefined, okay? Any other number you plug in, you get its reciprocal. So you flip 1 over 1, which you get 1. 2 would be 1/2. 3 would be 1/3, and so on. Okay. Now this graph actually takes us a while because we don't get to see a lot of points. So in this one, you have the point 1, 1, then you have the point 2, 1/2, and again, it's very difficult to graph because they're so close together. Okay. We could throw in a few more points. We could throw in some negatives. So the reciprocal of -1 is -1. The reciprocal of -2 again is -1/2. And so on. So again, that just gets us a few more points, -1, -1, -2, -1/2, and so on. Again, not quite a complete graph yet. Okay. It should seem obvious maybe that as you keep going, so if you plug in 4, you get 1/4, 5, you get 1/5, that this part of the graph just continues towards the x-axis, but will never hit the x-axis. So even when you get all the way out to 100, you'd be at 1/100th. Okay. It also behaves the same way over here. So the more negatives your number become, the closer you get to 0, but you won't hit 0. Okay. We're still missing a bunch between -1 and 1. We know we can't plug in 0, but it might be worth sort of checking a few numbers before -1. So I'll continue my table over here. So if I plug in 1/2, remember the reciprocal of 1/2 is 2. If I move even a little bit closer to 0, I get 1/3. Its reciprocal is 3. So as I move left towards x equal to 0, my outputs just keep getting bigger and bigger. So as I move back here, again, 1/2 you're up to 2, 1/3 you're up to 3, and so on. And again, you'll just continue back. But again, you can never hit the x-axis, because if you plug in 0, that's undefined. Okay. And then a similar thing happens here. Okay. Again, we look at these graphs much more in chapter 4. But again, this idea of having a line, in this case I have 2 lines, each axis acts as what we call an asymptote. An asymptote is just a line that a graph gets closer and closer to. In this case, at the ends, the left end and the right end, the graph is getting closer to the x-axis. So again, the x-axis would act as an asymptote. Okay. Similarly, near the middle of the graph, the y-axis acts as an asymptote. So the closer I come to 0 from the left, my outputs drop towards -infinity. When I approach 0 from the right side, when I approach x equal to 0 from the right side, the outputs shoot towards infinity. Okay, so we get a graph like this. Domain and range. Again, the only thing we can't plug in is 0. So we, again, using interval notation, we go through 0, up to 0, put a parentheses. Parentheses, remember, means not included. Union everything after 0. Okay. And then similar for the range. So again, we have all the numbers down here being hit, but we jump over the x-axis. So we jump over y equal to 0. So my range, again, you have to jump over 0. So put a parentheses there. That means 0 is not included, and then I pick up right after 0. All right, and then finally, the last function, again, sort of a different function we don't use very often, but it's nice to see a function that behaves very differently than some of the other ones. Greatest integer function simply spits out the integer, the greatest integer less than or equal to the input. Okay. Well, if you plug in an integer, then there's no problem. You get out that integer. The more interesting parts happen when you plug in fractions. So again, let me extend my table here a little bit. So let me just start out with some positives. So if I'm at 1.7, the biggest integer less than or equal to that would be 1. So again, it's not rounding, it just brings you back to the integer to the left. So if I go to 1.9, I'm still at 1. If I'm at 1.1, it goes back to 1. Okay. Once I jump past 2, so if I go to 2.1, then the graph will jump up to 2. Okay. It'll stay there when I get up to 2.7 or 2.9. Okay. We can also do a few between 0 and 1. So again, think of fractions like a half or 3/4. Okay. All of those would get pulled back towards 0. That's the integer less than or equal to it. And then negatives, again, just be careful that you remember you're going to the left. So if I have negative 1.7, it gets pulled back to negative 2, remember. Negative 2.4 gets pulled to the left, which would be, it will wind up at negative 3. Okay. This is also sometimes called the step function, and you'll see why. So all the fractions, so I'm going to start with these. If your input's between 0 and 1, so 0, 1/2, 3/4, you always stay down at 0. So we'll stay here. And then once we get to 1, we're going to jump up to 1. And so remember, at 1, you're 1, and for all of these, you stay at 1. So everything between 1 and 2, for x inputs, the output stays at 1. Once you get to 2, you jump to 2, and so on. Okay. And then this pattern continues all the way. It's a different kind of function. It's a function that only outputs integers. When you can't count fractions or decimal parts of something, if you're just counting whole numbers or integers, sometimes we'll use the greatest integer function. Okay. For domain and range, domain is still all real numbers. You can plug any number in you want. The range is a little bit tricky because notice for the output, you're only getting integers. Okay, so we can't use interval notation because remember, interval notation gives you a range of numbers. Okay, we keep jumping over all the numbers between 1 and 2 and all the numbers between 2 and 3 and so on. So most of the time for a range, you'll just write all integers. Can't really write this one in interval notation.